Now let's talk about another abrasive machining process. This is called as ultrasonic machining. We are still using some little abrasive particles, but this time our approach is a bit different. What we do, we have a special, let's say, tool, and this is called a sonotrode. And the thing is that it's vibrating at very high frequencies. It's usually around 20 kilohertz. And the thing is that its amplitude is very low. But the issue is that here, as you see in the sketch, we have abrasive particles in between the workpiece and the tool. So during this high frequency motion, low amplitude motion, we are actually hitting these abrasive particles with the tool, and then these particles are hitting the workpiece and trying to remove material from the surface. So with the help of this motion, we have high stresses on the workpiece, and once the stress is high, you'll have little cracks and some material will be removed from the workpiece. And thinking about this ultrasonic machining is that for various holes, various types of, let's say, shapes you're going to produce, you need to change your tool. For instance, if it is a rectangular, then you can only produce such rectangular shapes. For instance, this part is okay. If you have a kind of a rectangular shape, all these openings can be obtained with the help of the same tool. But if you want to obtain such circular holes, then you need to change the tip of your tool. The upper parts may be the same, but you need to modify the tip of your tool so that different shape holes can be obtained. And when do we use them? When do we use such a machining process, ultrasonic machining process? When the workpieces are quite harder and they are brittle, we may go with this process. And this is the thing I mentioned. We also have the rotary version of it, rotary ultrasonic machining. It's a bit different since in the previous one, we have a water slurry, and inside this water slurry, we have the abrasive particles, but this time we don't have it. Instead, we have a specific tool which has actually diamond abrasive particles embedded into this tool. And what this tool is doing again, it's vibrating ultrasonically, and also it is rotated. And furthermore, while doing these motions, it's also pressed against the surface at a constant pressure. So once you have these, then you can start to do the machining process. And it's very similar to face milling operation and mostly utilized to remove material from the top surface. And we can also use this process to open very deep holes having very high length to diameter ratios. And another important property of this process is that it has a bit higher material removal rate, especially in the ceramic materials. Now we are done with abrasive machining processes. From this point on, I will be talking about some finishing operations. In some of these, we may be using abrasive particles, and some we don't use them, but I think in most of them, there are some kind of abrasive particles. Let's have a look at the first one. This is called as coated abrasives. This is an example of it. So very primitive type of operation, finishing operation. We have a kind of a sandpaper, and on top of the sand, we have some abrasive particles embedded. They are bonded to this paper or some kind of cloth. So what we do, we may move it over our surface and try to increase the surface quality, remove little material. So in finishing operations, we are using less material compared to other abrasive machining operations we discuss. Our main focus is on the surface quality. This shiny surfaces can be obtained with such finishing operations. Then we have belt grinding, very similar to coated abrasives. The difference is that we have a belt and probably it's being rotated with the help of an electrical motor. So with the help of such an arrangement, the material removal rate might be improved, so we can use it especially in some production, mass production processes. Then we have wire brushing, and this is a bit special process in this wire brushing. we have again a rotating actually kind of tool, and around this rotating tool we have some wires, and with the help of these wires we try to actually remove material from the outer surface of workpiece and try to obtain some special patterns, special textures on the outer surface. Then we have another important finishing operation. This is called as honing, and you can see here a special honing tool. This is a spindle, and at the tip of the spindle, as you see, we have some stones. These stones are responsible for the finishing operation. They are usually made of some special materials, and the main aim of honing process is actually improve the surface quality of the holes. So after reaming process, maybe you can, or boring process, you can do honing to improve the surface quality and increase the accuracy of your holes. And obviously, while we are feeding our honing tool into the hole, we also rotate our honing tool, the stones, so that we will be removing a bit more material, and the quality of the interior hole, the interior surfaces will be improved. Another thing is that in some of the honing tools, you can adjust the position of these stones so that you can accommodate a bit larger holes. And if you use a bit smaller stones, then the process called actually super finishing. And we have an example sketch here. This time, we are not actually doing the operation inside the holes, but we do it on the cylindrical surfaces. We have a reciprocating motion. It's moving over the surface, but we try to actually not use the same path. Since if you use the same path, then we will be removing material from the same region, same grooves. So then if that is the case, the surface roughness will be increased, and then that will not be a finishing operation. So we are trying to rotate a little bit so that we will not have such grooves along the axis of our workpiece. Then we have another finishing operation. This is called as lapping, and the tools are called, or the softer materials we are using in this process are called as lap. So what we do in this process, we try to embed some harder abrasive particles into this soft material, which is lap, and then we hold this lap and move it over our workpiece and try to increase the surface quality. You can see this process here. So before we do the lapping, this is the workpiece. So you see we have volleys, we have heels, and this is our lap. It's a bit softer material, and we put some abrasive particles in between the workpiece and the lap. So once you start the operation, then the abrasive particles will be embedded into the softer material, and you move it. Once you are moving it over the workpiece, these abrasive particles will be removing material from the workpiece, and after the process you will have such a better surface. And if you want to do it on a machine, then you may place many workpieces on the table, on a rotating table, and then use again a softer tool as the lap. And once you have again relative motion in between the workpiece and the tool, you can increase the quality of these surfaces at a time. Then we have polishing. Actually, it's a bit different process with respect to other finishing processes. With the help of this polishing process, we obtain smoother and lustrous surfaces. So how we do it, we have some friction in between the tool and the workpiece. And once you have it, then the temperatures will be increased a little bit. And we try to obtain such shiny surfaces with the help of this frictional heating. And also, if you have some bumps, they may be removed from with the help of the smearing action. So this is a nice process if you want to especially obtain shiny appearance on your workpieces. Then we have a different version of this polishing process called as chemical mechanical polishing. We mostly use it in the semiconductor industry, while we are producing some chips. And as the name implies, we need to use some chemicals in the environment. So it's very similar to polishing. In addition to polishing, we add some chemicals in between the workpiece and the tool actually. Then with the help of these arrangements, we can increase again the quality of such actually items which are used in semiconductor industry. So in such process, obviously, since we have some chemicals, we are trying to do some actually corrosive action. So we can say that in this process, we have some amount of abrasion and some amount of corrosion. Then we have another finishing process called electropolishing. It is actually the reverse of electroplating. We are not adding material, but we are removing material from the workpiece. But this time, we are not contacting with the workpiece. This is a no mechanical contact type of finishing process. So that's why actually it's most suitable for irregular or smaller workpieces. And then we have the last finishing operation as the buffing, somehow similar to the polishing process. The only difference is that we are mostly using very soft materials as a disc. I mean, even they may be made of clothes or hide, but the rest, the fundamentals are the same. And since you are using softer materials, the resulting surface will have better surface finish. Now let's briefly talk about deburring operations. The burrs are actually the little triangles we obtain after the machining operations. And since they are not useful, they interfere with the assembly operations. They might be sometimes a kind of a safety hazard to the person handling these parts. So that's why actually we need to find some ways to remove these burrs on the surface of our parts. And even once you have too much burrs, they may even decrease the fatigue life of your component, and you need to pay more money on the fabrication of new products. So let's have a look at some deburring operations. There are various types of them. They are listed here. You may do it manually, remove manually, do autosonic machining, use some eraser bells. But I would like to focus on two types of them. The first one is thermal energy deburring. It's a quite interesting process. What is done here that you have a kind of a chamber. You put your workpieces having burrs on the edges, on the surface, and then you actually inject some a kind of a mixture of natural gas and oxygen. And then once you do the ignition, then suddenly you have a huge amount of heat generated, and the temperatures of the bursts will be increased to about 3000 degrees. And once it's increased to these very high levels, then they will be evaporated, but the temperature of your larger workpiece will be around 150 degrees. So obviously it cannot be melted or evaporated. So since the volume of the bursts are very little, so that's why with such a burst of heat, you can easily evaporate them and remove all of the burrs at a time. And the other option is using robotic arms. You see, we have an example here. So you have a grinding wheel, and then by doing a proper programming, you can remove the burrs from the workpieces by using such an robotic arm. Let's talk about the economics behind these finishing or erasing machining operations. Once you actually do extra finishing operations like super finishing operations, obviously the cost of your overall machining will be increased. And as you see, depending on the desired surface roughness value, for instance, if it's around, let's say, 2 to 3 micrometer, then it's about, let's say, 50%. But if you apply grinding or honing operation, as you see, the cost has increased by 3 times or even 4 times. And the result is that your surface roughness value will be less than 1 micrometer, around some nanometers.